Over to you, Ravi.
Okay, so thank you. So first of all, I would like to thank Suraj and other organizers for giving me this opportunity. So all right, so today I'm going to talk about some combination theorems for convergence groups. And as a consequence, we will also have combination theorems for relatively hyperbolic groups in some special cases. But most importantly, we will have the description of Bowditch boundary. So, all right. So this talk will be based on my recent work. So I will start with the definition of convergence group. So this notion of convergence group was introduced by Gehring and Martin, I guess, in 1987. So it was defined for Klein group acting on ideal sphere of hyperbolic space, but later Tukia generalized it to the compact out of spaces. So now we have the definition, the general definition is due to Tukia. So a group G acting on a compact metrizable space X is said to be a convergence group, with the following hold. So given a sequence Gn of drifting point in the group G, there exists a subsequence GNS and 2 points AB. So they need not be distinct, they could be same, such that for any compact subset K in the complement of B, if we apply this subsequence GNS onto this compact subset, so it should converge uniformly to B, and similarly for the inverse of the subsequence. So if you take any compact subset in the complement of A, it should converge to B. Yeah, it should converge to A, yes. So this example of convergence group, there are plenty of examples. The first one is hyperbolic group. So given a hyperbolic group, we always have this compactification by the Gromov boundary. So we have a natural action of hyperbolic group on its Gromov boundary, and it turns out that the reaction is in fact a convergence action. And similarly for relatively hyperbolic group. And so in case of relatively hyperbolic group, we again have this action on its so-called Bowditch boundary. I will define those things. So yeah, and a finitely generated group with a non-trivial fluid boundary. The Carlson, there is a paper by Carlson where he has proved that this, whenever you have a finitely generated group G with non-trivial fluid boundary, then the natural action of the group on its fluid boundary is a convergence action. So here fluid boundary means that suppose you are given a finitely generated group G, we take its Cayley graph and then we rescale its Cayley graph. So in the Cayley graph we take this age length to be 1. So but we rescale. So we are not scaling there by arbitrarily. So there will be some scaling function which satisfies some property, and by that function we rescale this length of edges, and by rescaling that, after that we will define a new length metric on the Cayley graph, and then take the Cauchy completion, and then we will have this fluid boundary. All right. But after that, we define this conical and parabolic limit point. So let G be a group acting as a convergence.
Ravi, if I may interrupt, there is a question by Andrew Krenz. What does it mean for a sequence of subsets to converge to a point?
Because this is converging uniformly, you can think of this if you take this neighborhood of neighborhood around this point B. So this sequence, if you apply this subsequent GNS on this compact subset K, so this should contain in that neighborhood, and this should be true for every neighborhood. There will be some constant capital N. After certain stage, it should converge. It should lie inside that neighborhood. If you take any neighborhood around it.
And there is some typo in this definition also. A should be changed by B. In this definition, yes. Yeah, so GNS of K converges uniformly to A.
Oh, yes, yes. This is what I was thinking, that there is something this. I think yes, you're right. There is a typo that this converges to uniformly to A, and the inverse will converge uniformly to B. Yeah. And they are called this attractive and repelling point, respectively. So an element of this group G is said to be loxodromic. So if G is of infinite order and has exactly 2 fixed points. and a point x is said to be a conical limit point. So if there exists a sequence, again a distinct point in G and two distinct point A and B, says that this G and X, this sequence, this should converge to A, and for all point X prime not equal to X, they should converge to B. So now then we have this definition of this parabolic point. So a point P in this space X is said to be parabolic if there exists an infinite subgroup of G which does not contain any loxodromic element and fixes P. Such a subgroup is called parabolic subgroup, and the stabilizer of P is called a maximal parabolic subgroup. So now we have this definition of this bounded parabolic point. So a parabolic point is said to be bounded parabolic if you take the stabilizer of this parabolic point, it's maximal parabolic subgroup, and it should act compactly on the complement of parabolic points. So it means the quotient should be compact. Right.
Yeah, Ravi, if you can hear us, you're not really audible.
Can you hear me now? Hello?
Yes, yes, we can hear you.
Yes.
Okay. So sorry for that. The internet is not stable. So now I stop the video and let's see. So a group G is said to be hyperbolic relative to a family P of subgroup if this group G admit a proper discontinuous isometric action on a proper hyperbolic convergence, and not only that, this every point of this boundary is either a conical or bounded parabolic point, and the subgroup in this family P are the maximum parabolic subgroup. All right, so in the of this sometime we have this plenty of exist, but it is relatively hyperbolic with respect to the free factor. And you can take this, it will relatively hyperbolic. And this the standard one, this example fundamental group of the complete finite volume Riemann element with pinch sectional curvature. So mentioned so if we have to select metrizable space X as a convergence group, then we say that G is have to be geometrically finite if every point of X is either conical, a midpoint, or bounded parabolic point. Firstly, Yemen characterize the relative hyperbolicity. So which says that let G be a group acting geometrically finitely on a non-empty perfect compact metrizable space. Just take the P be a set of representative conjugacy classes of maximal parabolic subgroup, and G is hyperbolic relative to P, and M is equivalently
There seems to be some problem again.
Is it fine now? Can you confirm? Can anybody confirm?
Yes, it's better now.
So now I'm going to give some syntax that's been enough to improve a famous combination theorem for graph of hyperbolic groups. Then later in 2003, the Hamini proved a combination situation when the action of the fundamental group of the given fundamental group of graph of group on its bacillatory is cylindrical, and the second one is the condition the age group should be fully quasi-convex in the adjacency. If you take 2 points in the bacillatory which whose distance is bigger than or equal to k for some constant k, so their point-wise stabilizer should be finite. And if fully quasi-convexity means, first of all, they should be relatively quasi-convex. So relatively quasi-convex subgroup means and they should act on its limit set geometrically finitely, and there is one extra condition on this limit set, on the translate of the limit sets, so which will imply that they are fully quasi-convex. So I haven't defined the full definition of the fully quasi-convex because I'm not going to use that. But in 2008, this Mahan and Reeves, this Mahan MJ and Lawrence Reeves, they proved a combination theorem for graph of relatively hyperbolic group, and this is the so far the most general theorem for this combination theorem for relatively hyperbolic groups. So they have generalized this Besswin-Affine combination theorem. So Besswin-Affine, they have proved this combination theorem for tree of hyperbolic spaces, and in the same way they have generalized to the tree of relatively hyperbolic spaces under some natural conditions. In 2014, this Alexander Martin, he has proved a combination theorem for L complexes of hyperbolic groups. So this was the history, but for us the most important combination theorem for this talk is this the Hamini combination theorem for relatively hyperbolic group. So what is that? It says that let G be the fundamental group of an cylindrical graph of relatively hyperbolic group with fully quasi-convex age group. And not only that, here in this theorem, he explicitly had described the Bowditch boundary and the parabolic structure, how we are getting the parabolics. So there, the Dhamni constructed a compact metrizable space M on which there is a natural action of the group G. Then he showed that the action of G on this constructed space M is geometrically finitely, hence by the theorem of Asli Yaman, the group G is a relatively hyperbolic group and M is homeomorphic to Bowditch boundary. But the problem is that from his theorem, if you remove the hypothesis that vertex groups are relatively hyperbolic, phase groups are fully quasi-convex, then it is unclear that G is a convergence group, even if you remove this cylindrical hypothesis, because the point was that this eccentricity forcing that we cannot flow a boundary point very far. But so we ask the following question: this let G be the fundamental group of a graph of convergence group with dynamically quasi-convex each group. So under which condition is G a convergence group? So we answer to this question in the following two situations: when the edge groups are parabolic in adjacent vertex group, and when the edge groups are cyclic. So now this is the definition of this dynamically quasi-convex subgroup for the convergence group. So let G be a convergence group acting on a compact domain. So a subgroup is said to be dynamically quasi-convex if the following set is finite. Take this coset, and this lambda is the limit set of H, this compactum X, and this should be finite for disjoint closed subset K and L of X. All right, so now these are the main result that we are able to prove this. The first theorem that let G be the fundamental group of a finite graph of convergence groups, so that the edge groups are parabolic subgroup of adjacent vertex group. Then G is a convergence group, and one can also prove that this whenever G is a convergence group, then the vertex group will be dynamically quasi-convex. And moreover, if the vertex group are geometrically finite, then G will also be geometrically finite. So using this theorem, we immediately have the following this corollary. Let G be the fundamental group of a finite graph of relatively hyperbolic group, such that the edge groups are parabolic. Then G is a relatively hyperbolic group. So, and we also have the description of this Bowditch boundary by the proof of the above theorem. So we will see that how we are constructing this thing. So we also answered that question in the following situation also. This is theorem that G be the fundamental group of a finite graph of torsion-free convergence group with dynamically quasi-convex. This time we are taking this cyclic H group. Then again G is a convergence group. Okay, so we immediately have this one application that since we know that the undistorted subgroup of finitely generated group with non-trivial fluid boundary is dynamically quasi-convex. So this is the result due to Yang. So then we immediately have this following corollary that G with the fundamental group of a finite graph of group where the vertex group are finitely generated torsion free with non-trivial fluid boundary, and the edge groups are infinite cyclic undistorted in the adjacent vertex group. Then G is again a convergence group. All right. But for relatively hyperbolic group, we have the following that G with the fundamental group of finite graph of relatively hyperbolic group with cyclic H groups, then G is again a relatively hyperbolic group. So now for proving this theorem, we are constructing some. First of all, we construct some set, and then we'll define a topology on that, and then we will prove that the natural action satisfy the condition for being a convergence group. All right, so this is the construction of this space. So in the proof of this theorem, we construct a compact metrizable space on which there is a natural action. But we will restrict to this amalgamated free product case. So let G be the amalgam of G1 and G2. Here G1 and G2 are convergence group and P is parabolic in both G1 and G2. So let T be the Basset tree for G and for a vertex V in the Basset tree that we denote this. We are fixing some notation. G with the stabilizer of V and G is the stabilizer of the edge E and tau with the fundamental domain for the action. And let this XV the compact metrizable space that GV act on XV as a convergence group. So now this we are defining this our set, our candidate set. So this is the contribution for the vertices from the Basset tree. We define this omega to be this G cross decision union of XV, and we are coming from the this vertex set from the fundamental domain, and it is divided by the natural relation. So what does this relation do? This relation is doing nothing but by this relation we have the disjoint union of this spaces corresponding to the vertices of Basset tree. So we have the disjoint union of the compactum on which the vertex group are acting as a convergence group. All right, so then how do we glue them together? So this is the contribution of the edges. Since each edge group embeds as a parabolic subgroup, so its limit set is singleton. So for each edge, we have this this just inclusion, this x from xe to xvi. Xe is just singleton. This is just parabolic point. So then we can define equivalence relation. Omega, the point, if you take 2 point x and x prime in, let's say xv and xv prime, they are equivalent. There should be an edge E joining v and v prime and a point, a parabolic point, and which satisfies simultaneously this condition. So then we have some pictures look like something like this. So here the circles are denoting the vertex spaces, compactum, and we are going along this parabolic point. So we will have the picture something like that. And we are also adding this in this omega mod tilde to this the boundary of Basset tree. So let this del t be the visual boundary of the Basset tree. Then we define this m prime as a set, the disjoint union of this del t and omega mod tilde. So this space will look like something like this. But this is not our candidate set. So for that we will need to define this domain. If you take any point x in omega mod tilde, we define domains to be the subtree of Basset tree. There we can flow that point. So we also define the domain of a point xi in the boundary of Basset tree to xi itself. So for getting the desired space, we further define an equivalence relation on this set m prime. So first you observe the domain of each point in omega mod tilde is either singleton and infinite subtree of the Basset tree. Infinite will be only for parabolic point for each group. If there is a point which is not in the edge, which is not the parabolic point, so its domain will be just one point. We cannot flow that. So we further identify the boundary point of infinite domain dx in del t to x itself. So again we will have this set. So far we are dealing with sets. By considering the equivalence relation generated by these relations, we denote this quotient of m prime by m. So again it will be the disjoint union of the two things, omega prime and del t prime. So now this is our candidate set. And then we define this definition of neighborhoods, how we are going to define the topology on this set M. So for that, we just look at the vertex V and take an open subset U of XV. XV is a compact metrizable space. So just take an open subset and we define this subtree, this T VU. And so this is a subtree of T. So suppose we want to include some vertex of Basel tree in this subtree. So what do? We just look at the geodesic joining V to W and look at the first edge, E, let's say. And if the parabolic point of this corresponding to that edge is already in this open subset U, then we will include that vertex in this subtree. And we will do the same thing. So if you for each vertex V in T, let us choose this countable basis of neighborhood of XV. And without loss of generality, we can also include the full space in this UV. So now I'm going to define the neighborhood around this point X in the omega prime. So for that, we just look at its domain. So it will be just VI. And for each I, we just take an open subset in XVI. It is an element of UVI containing X. And we also assume that UI equal to XVI for all but finite element indices. So then this neighborhood WX, so it is the disjoint union of three subset. So here we are defining this ABC as follows. So A will look like this. We just look at this subtree T VI UI and take the boundary point and look at all the intersection, and then further we take the intersection with this del T prime. So it will be a subset of this del T prime. So and B will be all those points in the complement of the union of XVI. So XVI are the compactum corresponding to the domain of the point X. So such that this domain of Y should be sitting inside in the intersection of T, VI, UI. And C is nothing but just a union of UIs. So these neighborhoods are actually the most important thing to understand all the proofs. So how the neighborhoods look like. So after that, so now we define the neighborhoods around the point of del T prime. So let us take a point xi in del T prime and fix a base point. So look at the geodesic ray in the Basel tree joining V0 to xi. So it is containing all those vertices W, joining the geodesic V0 to W, and take the intersection with the geodesic ray V0 to J. So its length should be bigger than point J of this del T prime. So and again, this you need to see that this definition of 215 by this does not depend on the choice of this point. We consider the smallest topology. So that is subset. And with this topology, we can show that we are able to a compact mean, but actually the fundamental proof of this. The effect on this. So now we have this space and has so it requires a proof. So it requires two technical able to use every point in particular from the are able to that is G is a convergence group. But now we assume that each vertex group are geometrically finitely on a compact metrizable. In this GV, every which is immediately bounded parabolic for the full group. So by this, we G is also vector geometrically finitely on this compact spectrum M. Have shown we have not proved anything, but by following this step, we are able to prove that G will also act geometrically finitely given the vertex group are geometrically finite. So after that, so by the above discussion, we have the following that G be the fundamental group of a graph of relatively hyperbolic group with parabolic edge group, not necessarily maximum. Then G is a relatively hyperbolic group. So we immediately have this result because the relatively hyperbolic group are anyway this geometrically finite, act geometrically finitely on its Bowditch boundary. And we will do the same thing, the same construction as we did for this in case of convergence group, and we will have the description of Bowditch boundary. So as a simple application, we have this, let G be a graph of relatively hyperbolic group with a parabolic edge group. And just take a subgraph of Y and consider the subgraph of group. Then one can show that this fundamental group of GY1 is a relatively cosine subgroup of fundamental group of GY. So here is a sample example. For example, you take this amalgamated field product of these two group G1 and G2. Both are relatively hyperbolic with respect to the P1 and P2. We are assuming there is only one subgroup P1 and P2. And suppose P is isomorphic to the subgroup of P1 and P2. So then by our result, G is relatively hyperbolic with respect to this parabolic P1, this amalgam P1 and P2 over P. And we also have the description about this boundary. So I am stopping by this to putting two questions: that is there an example of non-elementary convergence group which is not relatively hyperbolic? And the second question, is there an example of non-elementary convergence group which has trivial fluid boundary? Okay, so I'm stopping with this. Thank you. So here are some references. So all right, I'm stopping here.
Let's thank the speaker. Any questions for Ravi? So about question one that you gave. Yeah. So does your theorem say, or your proofs method say something about whether this may be true?
No, we haven't said anything about this question because it is completely open. That is there any example of non-elementary convergence group which is not relatively hyperbolic?
Okay.
And actually this answer to the question 2, if we are able to find a non-elementary convergence group which has trivial fluid boundary, then immediately we'll have the answer to the question 1. If we are able to find this.
Okay.
But they are thick groups, thick graph and thick groups. So they have the trivial fluid boundary. But even in that situation, we don't know whether they are non-elementary convergence group.
Other questions? Okay, if not, let's thank the speaker again.
Thank you.